India. Thank you for accepting our invitation, sir.
This call is now being recorded.
I also welcome all the participants who are more interested to attend the webinar on fiber reinforced concrete. Thank you all. Now I invite coordinator Mr. Veerabhatran to deliver the address on chief guest profile. Thank you.
Very good morning to one and all. It is my great privilege to introduce Professor Dr.G.S.THIRUGNANAM sir, resource person of today's webinar. Dr.G.S.THIRUGNANAM sir was graduated in civil engineering from Madras University in 1982. Then he obtained his master's degree in structural engineering from Anna University, Chennai in 1984. He received his prestigious PhD degree from Bardiyar University in the year 2002. He has 34 years of teaching experience and 20 years of research experience at IRTT Erode, which is one of the topmost institutions in Tamil Nadu. Then he has 2 years of teaching and research experience in Builders Engineering College Erode. He has published 41 research papers in international and national journals and presented more than 100 research papers in conferences. He is a life member in Indian Concrete Institute, Indian Society for Technical Education, International Center for Fiber Reinforced Concrete Composites, Institution of Engineers India, Institute of Urban Transport. He has guided more than 100 ME projects and 12 PhD scholars. His area of interest includes concrete technology, special concrete, seismic behavior of concrete, steel and composite structures, repair and rehabilitation of structures. He have successfully completed many consulting works like concrete mix design for buildings, design of highway bridges, rigid pavements, and consulting on canal linings. He is a reviewer and editorial board member in reputed journals like International Libraries, fracture mechanics study member and Erode University, Karpagam University, Darul Islam University, Cornea University, and many autonomous institutions. He has delivered number of seminars on the topic role of civil engineers, earthquake resistant design of structures, special concretes, repair and rehabilitation of structures, structural design, and NDT methods. Presently, he is working as professor in civil engineering department at Builders Engineering College Erode. We are very happy to have such great personality as our today's speaker. Now I invite Dr. G.S.THIRUGNANAM sir to present the session. Welcome, sir.
Thank you. Thank you. First of all, I wish to thank the organizers of this webinar and the management of your institution, Dr.N.G.P College, for giving this opportunity to present my thoughts to the audience. Let us go to the session. Screen visible? Okay, I think all of you have the view about the slide. So, slide visible?
Yes, sir.
All right. Okay, thank you. Thank you. Today, my topic is the recent developments in fiber reinforced concrete. You know that the concrete is the most widely used construction material, but it has several limitations. Particularly, it is weak in tension, has limited ductility, and little resistance to cracking. Its permeability to liquids and subsequent corrosion of the reinforcement is very, very high, and poor resistance to sulfate attack or some other major deficiencies. So extensive research in the field of concrete technology has led to the development of special types of concretes which can eliminate to a great degree these basic deficiencies. One of the development is fiber reinforced concrete. Fibers are added to the concrete to control the cracking caused by plastic shrinkage and drying shrinkage. So whenever you pour the concrete, this excess water has to be dried out by evaporation. Because of this, plastic shrinkage and drying shrinkage has taken place and cracks have been developed at the surface of the concrete. This has to be controlled by means of fibers. The addition of small closely spaced and uniformly dispersed fibers will act as crack arresters and enhance the tensile strength, fatigue strength, impact strength, and abrasion resistance of the concrete. They also reduce the permeability of the concrete. Though the flexural strength may increase marginally, fibers cannot totally replace the flexural steel reinforcement. So these fibers are added only as a secondary reinforcement, not replacing the main reinforcement. The presence of micro cracks at the mortar aggregate interface is responsible for the inherent weakness of the plain concrete. So for the concrete, the presence of micro cracks is very, very important for the weakness of the concrete. This weakness can be improved by inclusion of the fibers in the mix. The fibers help to transfer the loads at the internal micro cracks. The fibers help to transfer the loads at the internal micro cracks. Such a concrete is called a fiber reinforced concrete. Thus, a fiber reinforced concrete is a composite material essentially consisting of conventional concrete reinforced by fine fibers. The fibers suitable for reinforcing the concrete have been produced from steel, glass, and organic polymers. These fibers are available in different sizes and shapes. Fiber reinforced concrete is a two-phase composite material in which cement-based matrix is reinforced with ordered or random distribution of fibers. The distribution of fibers may be ordered distribution or random distribution. Fibers in cement-based matrix act as crack arresters, which restricts the growth of flaws in the matrix, preventing these from enlarging under the loads, into cracks which eventually cause failure. It can result in improvements in static and dynamic properties of the matrix. Use of mineral admixture, especially flares, silica fume, etc., become more popular after the usage of high-range water-reducing admixture, that is super plasticization. In FRC, these admixtures produce a denser mix, resulting in better mechanical properties of concrete. So fibers can be added directly to the mixture once the other ingredients have been uniformly mixed. So as usual, cement, fine aggregate, coarse aggregate with water has been poured into the mixer and usual mixing process is done. The fibers are added directly to the mixer itself. The transporting, polishing, and finishing techniques for the fiber reinforced concrete are the same as those used for the plain concrete, conventional concrete. The major factors affecting the characteristics of fiber reinforced concrete are water cement ratio, percentage of volume, percentage or volume fraction of fibers, diameter and the length of the fibers. There is one term called as aspect ratio. It is defined as the ratio of the length to diameter ratio. The length of the fiber divided by diameter of the fiber. From the research, the aspect ratio is around 80 to 100 is the optimum aspect ratio, and it can be adapted for all types of fiber reinforced concrete with the steel fibers. The location and the extent of cracking under the load will depend upon the orientation and number of fibers in the construction. So the location and the extent of cracking under the load will depend upon the orientation of fibers and number of fibers in the cross section. The fibers restrain the shrinkage and creep movements of the plain mortar, unreinforced metals. So this figure shows the fibers, steel fibers, different shapes of the steel fibers, hooped end or crimped end flat fibers. These fibers, hooped end fibers, are glued together to have a bunch, just like a stapler pin. This bunch of the fibers have been inserted in the water. It will be dispersed because the glue is vanishing, and the fibers are randomly mixed in the concrete. And wire fibers are there. Polypropylated polypropylene fibers, fine fibrillated polypropylene fibers, or glass fibers. These fibers are commonly used in fiber reinforced concrete. In contrast to reinforcing bars in reinforced cement concrete, which are continuous and carefully placed in the structure to optimize their performance, the fibers are discontinuous and are generally randomly distributed throughout the matrix. In reinforced cement concrete, the reinforcing bar is a continuous bar. The length of the beam means the same length of the bar is used as a tensile reinforcement or compression reinforcement. It is a continuous reinforcement. But in case of the fiber reinforced concrete, the fibers are discontinuous and are generally randomly distributed throughout the matrix. As a result, the reinforcing performance of steel fibers is inferior to that of reinforcing bars. In addition, these fibers are likely to be more expensive than conventional steel bars. This FRC is not likely to replace conventional reinforcement. FRC is not likely to replace conventional concrete. That means the fibers are acting only as a secondary reinforcement and not the primary reinforcement as the conventional reinforcement, steel reinforcement. However, the addition of fibers in the brittle cement and concrete matrices can offer a convenient, practical, and economical method of overcoming their inherent deficiencies. What are the inherent deficiencies? Weak in tension, limited ductility, more permeability, more resistance to chemical attack, more prone to corrosion attack, like this. These deficiencies can be overcome by use of FRC. Poor tensile and impact strength, and enhances many of the structural properties on the basic materials such as fracture toughness, flexural toughness, flexural strength, and resistance to fatigue strength, impact strength, thermal effect on spalling. These properties are given by the fiber reinforced concrete. Essentially, fibers as a crack arrestor, restricting the development of cracks and thus transforming an inherent brittle matrix, that is cement with its low tensile and impact resistance, into a strong composite with superior crack resistance, improved ductility, and distinctive post-cracking behavior. Post-cracking behavior prior to the failure. Steel fibers are probably the best suited for structural application. Due to superior properties like increased tensile strength, increased bending strength, improved ductility, resistance to cracking, high impact strength, and high toughness, and high energy absorption capacity, this fiber reinforced concrete has found special application in hydraulic structures, pavements, road pavements, airfield pavements, and bridge decks, heavy duty floors, and tunnel linings, etc. So these are the applications of the fiber reinforced concrete. In general, the superior toughness and energy absorption properties of FRC in comparison to conventional concrete, plain concrete, or reinforced cement concrete improve as volume fraction of fiber increases. Techniques for achieving high fiber volumes include the strategy of pre-placing fibers in the formwork and infiltrating the bed of fibers with a cementitious slurry, and this composite is called as slurry infiltrated fiber concrete. What is the mechanism of fiber matrix interaction? The tensile cracking strain of the cement matrix is very much lower than the yield strain of the steel fiber. The yield strain of the steel fiber is known, 0.002. So the tensile cracking strain of the cement matrix is very much lower than this 0.002 strain. As a result, when FRC is loaded, the matrix will crack long before the fibers can be fractured. When FRC is loaded, the matrix will crack long before the fibers can be fractured. Once the matrix is cracked, the composite continues to carry increasing tensile stress. Once the matrix is cracked, all the tensile stresses are transferred to the fibers, and the composite material FRC continues to carry the increasing tensile stresses. Peak stress and peak strain of the composite are greater than those of the matrix alone. During the inelastic range between the first cracking and the peak, multiple cracking of matrix occurs. During the inelastic range between the first cracking and the peak, multiple cracking of matrix occurs. So the cracking mechanism is multiple cracking mechanism. Until the initial cracking of the matrix, it is reasonable to assume that both the fibers and the matrix behave elastically, and there is no slippage between the fibers and the matrix. In RCC, we have assumed that one of the major assumptions, there is a perfect bond between the steel and the concrete. There is no slip of the steel from the concrete. The same assumption is here also valid within the elastic behavior. In elastic behavior, within the elastic limit, there is no slippage between the fibers and the matrix. After initial cracking has occurred, the composite will carry increasing load only if the pull-out resistance of fiber is greater than the load at the initial cracking. Pull-out resistance of the fibers, because of the bond strength, if the bond strength is exceeded, the fibers can be pulled out from the matrix. This pull-out resistance of the fiber is greater than the load at the initial cracking means it will continue to take the loads. In the post-cracking stage, the failure of the composite is generally due to fiber pull-out rather than fiber yielding or fracture. Fibers cannot yield or fracture. Before that, the fibers are pulled out from the matrix because of the little bond stress between the fibers and the concrete cement matrix. In order to improve this bond characteristics, the surface roughness of the fibers have been improved, that is by means of crimped fiber or hooked fiber, not hooked fiber, that is crimped fiber, a deteriorating shape, deviating shape. In FRC, the fracture is a continuous process where the cracking occurs over a wide range of loading and the debonding of fiber occur over several stages. The bond or pull-out resistance depends on the average bond strength between the fibers and the matrix, the number of fibers crossing the cracks, and the aspect ratio. The pull-out resistance depends on the average bond strength between the fibers and the matrix, the number of fibers crossing the cracks, and the aspect ratio of the fibers. Improvements in structural performance of FRC depends on the strength characteristic of fiber, volume of fiber reinforcement, dispersion and orientation of fibers, and their shape and aspect ratio. In FRC member, subject to flexure, the load at the first crack will increase due to the cracking mechanism of the closely spaced fiber. Load at the first crack will increase due to the cracking mechanism of the closely spaced fiber. After the concrete cracks in tension, the fibers continue to take the load provided the bond is good. When the fiber strain reaches its breaking strain, the fibers fracture, resulting in load transfer to the fibers of adjacent layers, which on reaching their breaking strain, the fracture and resulting in the shifting of neutral axis. As the conventional reinforcement, you know that under reinforced section, over reinforced section, balance section, etc. If we provide under reinforced section, the neutral axis has been shifting towards the top. Whenever the load is increased, the cracking has developed, etc. The load strain is transferred to the steel and the steel is getting yielding. The similar mechanism has been observed in FRC also. The load transfer to the fibers of adjacent layers, which on reaching their breaking strain fracture and resulting in the shifting of neutral axis. The failure occurs when the concrete in compression reaches ultimate strain. Similar to RCC, the ultimate failure is due to the compression failure when the strain in concrete reaches the ultimate strain of the concrete, 0.0035. When the compressive strain in concrete reaches 0.0035, the concrete crushes and it is. Before that, the steel is getting yielded and it will not attain the yield strain. The most important factors affecting the ultimate load are the volume of fibers and the aspect ratio. The fibers are classified into generally two types: artificial fiber and natural fiber. Artificial fiber, steel fiber, polypropylene fiber, asbestos fiber, glass fiber, carbon fiber, and polyester fiber. These are manufactured artificially. Steel fibers are most commonly used fibers, and glass fibers are also used in fiber reinforced concrete in special types of application because it is also a higher strength, high modulus of elasticity, etc. And polyester fibers are synthetic fibers, low modulus fibers, and these are commercially easily available from the petrochemical industries. So it can also be used to arrest the plastic shrinkage and drying shrinkage effects. This polyester fiber and glass fibers are used for arresting the cracks, but steel fibers are mainly used for the bridging action between the cracks and improving the ductility and the energy absorption characteristics. Polypropylene and asbestos are little bit used whenever it is needed. Natural fibers, coir fiber, sugarcane fiber, jute fiber, banana fiber, sisal fiber, etc. Vegetable fibers, it can be also called as vegetable fibers. It has very, very low modulus of elasticity and is low tensile strength. And this may be used, these natural fibers or vegetable fibers are used from immemorial days, ancient days, to improve the properties, the unity of the mortar or concrete. Just the fibers are acting as a crack arrestor. Commercially, it is explained by means of the mud mortar. If the mud mortar is provided with coir fiber or jute fibers or this banana or sisal fibers, and if the mud mortar is used for the plastering or the bonding purpose, jointing purpose, etc., whenever there is a crack, these fibers will take care of the cracks and it gives additional strength to the mortar. So this has been used from 200, 300 years back also. Types of steel fibers. Round steel fibers are produced by cutting round wires into short length. Cutting round wires means commercially 22 gauge wires or 24 gauge wires, etc. Steel wires are available. These steel wires may be cut into separate lengths, short lengths, say 4 centimeter or 5 centimeter, 2 centimeter, etc. That is called a round steel fibers. Alternatively, flat steel fibers are produced by slitting flat steel. Mechanically, the flat sheet is processed by means of slitting to produce the flat steel fibers. Commercially available fibers are mostly these flat steel fibers, plain fibers. Alternatively, deformed fibers or crimped fibers are produced for improving the mechanical bond between the fiber and matrix. The shape of the fiber is just like our hairpin. The surface of the fiber is having so many crimps, ups and downs. It will improve the bond between the fiber and the matrix. Another classification of the fiber is high modulus fiber, low modulus fiber. This high modulus fiber means steel, carbon, glass, because the modulus of elasticity of these fibers are very high, say 2 into 10 power 5 or 1 into 10 power 5, etc. But the vegetable fibers are low. Natural fibers or the synthetic fibers such as polypropylene, etc., is having very low modulus, some hundreds of MPa, not thousands of, 10 power 5, 10 power 3, thousands of MPa is there. High modulus fibers improve both flexure and impact resistance simultaneously, improve the strength properties. High modulus fibers improve the strength properties, whereas the low modulus fiber improve the impact resistance of concrete, but do not contribute much to flexuration. Low modulus fibers improve only the impact resistance and arresting the cracks, shrinkage cracks, etc., but do not contribute much to flexural strength. This classification of fiber reinforced concrete according to volume fraction. Low volume fraction of the fiber reinforced concrete, moderate volume fraction of fiber reinforced concrete, and high volume fraction of fiber reinforced concrete. If the volume fraction is less than 1, it is called as low volume fraction. If the volume fraction is greater than 2, it is called as high volume fraction. If it is in between, moderate volume fraction. Low volume fraction. The fibers are used to reduce the shrinkage cracking. These fibers are used in slabs and pavement that have large exposed surface, leading to high shrinkage cracks. This shrinkage cracks is normally witnessed on the top of the roof slab or top of the concrete pavement. That is the flat surface exposed to the atmosphere. This shrinkage cracks has been arrested by means of these fibers with very low volumes, say 0.25% or 0.5%, etc. For steel fibers, it may be 0.5%, or for other fibers, synthetic fibers and other things, etc., it may be 0.1%, 0.2%, etc. Dispersed fibers offer various advantages of steel bars and wires to reduce the shrinkage crack. The fibers are uniformly distributed in 3 dimensions, making an efficient bond load distribution. The fibers are uniformly distributed in 3 dimensions, making an efficient load distribution. The fibers are less sensitive to corrosion than the reinforcing steel bars. Less sensitive steel fibers. All the fibers are steel fibers. The steel fibers are less sensitive to corrosion because the steel fibers are not a continuous fiber, it is a discontinuous fiber. In between these fibers, the cement matrix is available. So there is no continuity of the rusting formation. So the corrosion is less. The fibers can reduce the labor cost of placing the bars and wires. Moderate volume fraction. The presence of fibers at this volume fraction increases the modulus of rupture, fracture toughness, and impact resistance. The presence of fibers at this volume fraction, 1 to 2%, 1% or 1.25, 1.5, 1.75, 2%, etc. increases the strength properties, modulus of rupture, fracture toughness, impact resistance, etc. These composites are used in construction method such as fiber shotcrete and in structures that require energy absorption capabilities, improved capacity against delamination, spalling of concrete and fatigue strength, etc. So this may be used for the fiber shotcrete used for tunnel lining or other purposes, tunnel purposes, and in structures that are situated in earthquake-prone areas or wind-prone areas, which require much more energy absorption capacity. So for improving energy absorption capacity, moderate volume fraction of the fibers are added. It also improves the capacity against delamination, spalling of concrete, and fatigue strength, etc. High volume fraction. The fibers used at this level led to strain hardening of the composite. The fibers used at this level lead to strain hardening of the composite. Because of this improved behavior, these composites are often referred as high performance fiber reinforced concrete, HPFRC. HPFRC, high performance fiber reinforced composite. In the last decade, even better composites are developed and are referred to as ultra high performance fiber reinforced composite. This involves high volume fraction of the fibers, more than 2% of the fibers. The mechanism. The composite will carry increasing loads after the first cracking of the matrix if the pull-out resistance of the fibers at the first crack is greater than load at first cracking. At the crack section, the matrix does not resist any tension and the fibers carry the entire load taken by the composite. With an increasing load on the composite, the fibers will tend to transfer the additional stresses to the matrix through bond stresses. This process of multiple cracking will continue until either fibers fail or the accumulated local debonding will do fiber pull. Either fiber fractures or the fiber is pulled out from the matrix. Until then, it takes increased loads. Because of this, the energy absorption is more. According to the report by ACE committee, the total energy absorption in the fiber debonding is measured by the area under the load deflection curve total energy absorbed in fiber debonding is measured by the area under the load deflection curve before the complete separation of fiber takes place. It is at least 10 to 40 times higher for fiber reinforced concrete than for the plain concrete. So plain concrete one and fiber reinforced concrete, it is around 10 to 40 times the more energy absorption capacity. The magnitude of improvement in toughness is strongly influenced by fiber concentration and resistance of fibers to polar weight, other factors such as shape or surface factor. The magnitude of improvement in toughness is strongly influenced by the fiber concentration and resistance of fibers to pull-out. Pull-out resistance should be more. Role of fiber size. The fibers are generally classified into two types, short fibers and long fibers. To bridge the large number of micro cracks in the composite under the load and to avoid large strain localization, it is necessary to have a large number of short fibers. The short fibers with a large number of quantities have to be provided in fiber reinforced concrete to bridge the large number of micro cracks in the composite developed under the load and to avoid the large strain localization. The uniform distribution of short fibers can increase the strength and ductility of the composite. Whereas the long fibers are needed to bridge discrete macro cracks at higher length. If you consider the behavior of RC beam under the load, first micro cracks have been developed at various places due to the flexural strength of the beam, concrete, and then all the load is transferred to the steel. Steel is getting yielding and elongates further and further. So cracks have been developed, macro cracks. The width of the crack is developed, that is macro cracks. Similarly, length of the crack is also propagated through the towards the neutral axis and towards the top surface compression. However, the volume fraction of the long fibers can be much smaller than the volume fraction of short fibers. So the volume fraction of the long fibers should be as low as possible, about 1% or less than. Whereas short fibers, it may be little high, 1.5 or 2%, etc. The presence of long fibers significantly reduces the workability of the matrix. That is a drawback of the long fiber. The presence of long fiber significantly reduces the workability of the mixed fiber reinforced concrete. So, in order to increase the workability, you have to add superplasticity, etc., or powder content. When well compact and cured, concretes containing steel fibers seem to possess excellent durability as long as fibers remain protected by the cement. These fibers are normally protected by the cement paste on the surface. So, inner surface of the concrete. This when well compact and cured, concretes containing steel fibers seem to possess excellent durability. So, the durability of the concrete fiber reinforced concrete is excellent. In most environments, especially those containing chloride, surface rusting is inevitable, but the fibers in the interior usually remain uncontrolled. You may ask a question: in the severe environment, especially those containing the chloride or salt extruder atmosphere, the surface rusting is inevitable. It cannot be avoidable. Surface rusting will form, but the fibers in the interior usually remain uncovered. Fibers at the exterior surface is usually get rust formation and corrosion, but the fibers in the interior portion remain uncorroded because cement matrix is there in between this exterior surface and the interior surface. Long-term tests of steel fiber concrete durability showed that minimum corrosion of fibers and no adverse effect after 7 years of exposure to de-icing sand. That is in America, an experiment shows that 7 years of exposure will not corrode the fiber reinforced concrete, etc. In our moderate or mild exposure condition, there will not be any steel corrosion of fiber reinforced concrete over service life. maybe 15 years or 25 years, etc. Glass fibers, this ordinary glass fiber cannot be used in Portland cement mortars or concrete because of the chemical attack by the alkaline cement base. Zirconia and other alkali-resistant glass fiber possesses better ductility, durability to alkaline environments, but even these are reported to show a gradual deterioration with the time. Glass is acidic material and alkaline cement concrete is alkaline material. These are reacting and ultimately the glass fibers are vanishing. After some times the glass, there is no glass fiber. It is completely deteriorated with the time. So the use of glass fiber will be avoided. Even alkali-resistant air glass fibers have also limited durability. Because similarly, most natural fibers such as cotton or wool and many synthetic polymers suffer from lack of durability to the alkaline environment of the Portland cement base. So, glass fiber use பண்ணக்கூடாது, natural fibers, vegetable fibers use பண்ணக்கூடாது. எப்ப durability எதிர்பார்த்தீங்கன்னா இந்த ரெண்டு யூஸ் பண்ணக்கூடாது. Only available fiber is steel fiber. This behavior by experiment, it can be proved that 25% increase in compressive strength for 60 kg per meter cube, that is less than 1% volume fraction. 25% increase in compressive strength. Whereas the flexural strength may be increased to 30% or 40%. 0.75% volume fraction and 90 aspect ratio produces 30% increase in flexural strength. The increase in fiber content results in increase in the energy absorption capacity as much as 100%. According to the report of ACA committee, steel fibers improve the ductility of concrete under all modes of loading. Either it may be compression, tension, shear, torsion, or flexor, etc. All modes of loading, steel fibers improve the ductility of the concrete. A concrete beam containing steel fibers suffers damage by single or multiple cracks with increasing difference. As I mentioned earlier, the fiber reinforced concrete or fiber reinforced concrete beam subjected to flexor exhibits a multiple cracking mechanism with increasing deflection before the failure. In glass fiber reinforced concrete, the mechanism that is primarily responsible for the strength and the ductility is fiber pull-out. Because the surface of the glass fiber is smooth, so it is more easily pulled out from the cement matrix. So fiber pull-out is the common phenomenon in glass fiber reinforced concrete. Polyester fiber used in concrete to control the plastic shrinkage induced cracking. So polyester fiber such as Recon 3S fibers can be used on FRC only to control the plastic shrinkage induced cracking. So what are the advantages of fiber reinforced concrete? Steel fibers result in more homogeneous mix in concrete. Flexural strain capacity is enhanced. Adds ductility to concrete. The controlled cracks. Joint stability is more. Narrow joint width is possible. Shear load is getting transferred. Better shear load transfer. Fatigue and impact resistance. Higher amount of fatigue resistance or impact resistance. Post-crack ductility is very much improved. It will not be available in RCC, but in fiber reinforced concrete, post-crack ductility is very much high. Reduces material consumption and saves cost. Because of the improved strength, the material consumption is reduced. Longer service life. Because of these superior properties, it has been applied pavements, airfields, and bridge decks, industrial and other flooring units subjected to wear and tear and attack due to chemical attack. This industrial and other flooring units subjected to wear and tear is best illustrated in Netaji Apparel Park, situated in Permanallur, located in Permanallur. The new textile park has been provided with the floor construction by means of fiber reinforced concrete. Here the fibers are Recon 3S fibers, that is polyester fibers are added. This improves the wear and tear resistance, that is abrasion resistance, and it will give longer life to the floor units because there are so many vehicles transferring the goods from one place to another place. So wear and tear is very high. To avoid that, there is industrial flow. Another is due to chemical attack. If the chemical is spilling, a salt or acid is spilling, and it will cause the corrosion. To avoid this, the surface of the concrete is made with FRC, fiber reinforced concrete with the centrifugal fibers. This application may be highway and urban improvements, hydraulic structures, tunnel linings, industrial floors, bridge jacks, refractory concrete, precast applications, structural applications, etc. The major advantage of using SFRC in hydraulic structure is its resistance to cavitation or erosion damage by high velocity water flow. Suppose take an example, Mettur Dam. The water is stored up to 120 feet. Now, if you open the shutter, the water is rushed through the gate and attacks the spillway, and the stilling machine causes the cavitation or the erosion. This particular damage has to be arrested by means of fiber reinforced concrete. So another slide showing the applications and fiber reinforced concrete, prefabricated panels, circuit, curtain walls, slabs and grade, precast elements, walls, etc. Pipes, composite decks, thin sheets, etc. There is another development of fiber reinforced concrete called as ductile fiber reinforced concrete. Ductile fiber reinforced cementitious composite. Ductile fiber reinforced cementitious composite is a broader class of materials that has properties and superior performance characteristics compared to conventional cementitious material such as concrete or conventional fiber reinforced concrete. Deforces have unique properties including damage reductions, damage tolerance, energy absorption, crack distribution, deformation compatibility, and delamination resistance. If the FRC is ductile, then it is called as ductile fiber reinforced concrete. Another is ultra high performance concrete. Ultra high performance concrete is a high strength, high stiffness, self compacting concrete and ductile material formulated by combining Portland cement, silica film quartz floor, finished silica sand, high range water reducer, water and steel or organic fibers. This high performance concrete UHPC is commonly reinforced with steel or organic fibers to improve their performance. That is why it is called as ultra high performance fiber reinforced concrete. The materials for UHPC are usually supplied by the manufacturers in a 3-component premix: powders and super plasticity and organic mix. This powder is containing a mixture of Portland cement, silica fume, quartz powder, and fine silica sand. This is pre-blended in bulk bags, available in 50 kg bag or 40 kg bags, etc. Once you open the bag and mixing with water along with super plasticity and the organic fibers or steel fibers are inserted, this produces ultra high performance fiber reinforced cement concrete. Another development, ductile fiber reinforced cementitious composite, slurry infiltrated fibrous concrete. SIFCON. SIFCON is produced by infiltrating cement slurry into pre-placed steel fibers in a form one. It has to be noted that it does not contain any coarse aggregate but has a high cementitious content. In SIFCON, even though it is named as concrete, there is no coarse aggregate inside. It consists of only cement and fine powder such as fly ash and fine sand, etc., less than 300 micron sands. So powder content, it has a size cementitious content. Slurry infiltrated matte concrete is another form, is similar to SIFCON but use pre-placed fiber mill. These fibers are discontinuous fibers. Here it is a continuous fibers. That is the difference. So slurry infiltrated fibrous concrete SIFCON, it is pre-placed in the mold to its full capacity, thus forming a fiber network. For example, if you take a cube, 150 mm by 150 mm by 150 mm, the capacity is 150 into 150 150 into 150, so many centimeters cube. The steel fibers are pre-placed in the mold to its full capacity, thus forming a fiber network. After that, the cube is completely filled with randomly oriented discontinuous fibers. This fiber network is then infiltrated by a cement-based slurry. This fiber network is then infiltrated by a cement-based slurry. Cement-based slurry means pure synthesis slurry, or cement plus fly ash slurry, or cement, silica fume and fly ash slurry, or cement, fly ash, silica fume, or GGBS, or any other cementitious material, along with quartz powder, etc. Only thing is, there is a powder material which is less than some 100 micron size. Due to this method of fabrication, the volume fraction of fibers can be very high, ranging from 4 to 20%. So the fiber volume is approximately 10% by the method of packing inside the mold. So it ranges from 4 to 20%. If you add a compact method of packing, then as much as 20% of fiber has to be filled inside the mold. Function of several parameters including size, shape, aspect ratio, orientation, and method of packing, and the extent of vibration. So the strength of the silicon or the properties of the silicon is a function of several parameters including size, shape, aspect ratio, orientation of fiber, method of packing, and the extent of vibration. Silicon is made by pre-placing steel short fibers followed by the infiltration of dense cement-based slurry. Since fiber orientation cannot be controlled, a much higher volume fraction is necessary to achieve behavior like that of silicon. It is manufactured by pre-placing continuous fiber mats followed by infiltration of a specially designed cement-based slurry. Just like chicken mesh and weld mesh, this steel fiber mesh is also available. Steel fiber mat is also available in layers. You get the roll and cut into the required length and spread this layer inside the mold. Cube means 15 by 15 square mesh is cut and it is arranged layer by layer up to its full volume, and then it is followed by infiltration of specially designed cement-based slurry. It results in SIMCON, slurry infiltrated matte fiber concrete. Because of this, the fiber mats are pre-woven and delivered to the site in large rolls. The mats need only to be cut and unfolded into the formwork. 5% volume fraction of silicon produces around 16 Newton per mm square tensile strength. Whereas for producing the same amount of tensile strength, we need 12% volume fraction of the steel fibers in silicon. So silicon is less costly than silicon, provided you have to get the steel fiber mats in large rolls from the factory. Now it is commonly available in India also. Silicon beams reinforced with mild steel bar reinforcement. As I said earlier, fiber reinforced concrete. Fibers are acting as only secondary reinforcement, not the primary reinforcement. So the primary reinforcement is provided by the longitudinal bars or the mild steel bars or tough steel bar reinforcement, have a much flexural strength and flexural toughness than that of condensed concrete. Silicon beam column connections absorb much more energy and sustain much higher loads compared to normal concrete. This will be illustrated by means of an experimental investigation. The energy absorption capacity is about 100% more than that of plain concrete or conventional fiber reinforced concrete. What are the typical properties of silicon? It also varies with the fiber volume fraction. If the fiber volume fraction is 4% or 6%, the unit weight of the concrete is about 24 kN per meter cube, just like that of plain concrete. But if the volume fraction of steel fiber is 10% or 15%, etc., then the unit weight of fiber reinforced concrete is much more, that is 32 kN per meter cube. But typically it is same as that of RCC. In RCC, we are assuming the 25 kN per meter cube. The same thing is assumed for the 5% or 6% volume fraction of the fibers. Typical compressive strength is about 200 Newton per mm square. You can attain the compressive strength of the silicon material as high as 200 Newton per mm. That is, this fiber reinforced concrete made with the silicon material is M200 concrete. Not only that, the other properties. Typical tensile strength is 14 Newton per mm square and typical flexural strength is 76 Newton per mm square. What about the typical tensile strength of ordinary plain concrete, RCC, ordinary concrete? It is about 1 Newton per mm square. For fiber reinforced concrete having 1% or 2% volume fraction, it may be about 2 or 3 Newton per mm square. But you compare that for silicon, it may be as high as 14 Newton per mm square. The flexible strength is 4 Newton per mm square for M20 concrete, or 6 Newton per mm square for M40, M50 concrete, or for fiber reinforced concrete having volume fraction of about 1%. But here it is 20 times greater, near about 80 Newton per mm square has been achieved by silicon. So large amount of flexural strength is available in the silicon material. It can be used for the flexural member structures such as bridges, long span bridges, or the beams, etc. Wherever flexural strength of the concrete is essential, you need the fiber reinforced concrete made with the silicon material. The other properties are also improving. 0.005 is the shrinkage strength, and 90% static strength up to 2 million cycles. That is the durability, aquatic strength. 90% strength up to 2 million cycles. In our laboratory, the experiment shows that for normal concrete, the cube strength is 32 Newton per mm square. For silicon, 46 Newton per mm square. For FRC, it is 37 Newton per mm square. For the cylinder compressive strength, 27, 31, 35. Spread tensile strength of the cylinder 2.6, 3.8, 7.6. 100% increase that of the fiber reinforced concrete. Flexural strength 4.5, 5.9, 28.4. 7-fold increase of the flexural strength than normal concrete, or about 6 times or 4.5 times greater than FRC. In literatures, it may be as high as 76 MPa, that is about 20 times greater than that normal concrete. Abrasive index, it is done using a Doris abrasion testing machine. The abrasion loss of weight divided by virgin weight into 100. It will give 66% for normal concrete, 40% for FRC, and only 18. Wear and tear strength is very high. Wear and tear resistance is very high. Suppose if we test for the impact strength properties by means of aggregate impact testing machine or any other impact testing machine, one blow is sufficient for breaking of the specimen in normal concrete, whereas it requires about 20 blows for fiber reinforced concretes, 20 times more than that. But for silicon, it is several hundred times, so 600 times more than that of normal concrete, or 30 times more than that of FRCs. That is the main advantage. The impact strength of the silicon material is as much as about 600 times. 600 times. It is particular advantages for the blast resistant structure or explosive resistant structures, etc., where impact values, impact strength is prevalent. Because of the superior properties, the various applications of the silicon include security bars that need protection against blasting, drilling, and fire, explosive resistant containers for storing materials that could accidentally explode. Because of the improved impact strength, about 600 times, there will not be any damage if it is accidentally explode. Repair of the structural components such as damaged pre-stressed concrete beams, bridge deck rehabilitation, pavement rehabilitation, abrasive resistant surfaces in places such as scrap yards, etc., precast products for rapid repairing, refractory applications, etc. The main application is for the bridge deck rehabilitation. For example, If we take the busiest bridge, say London Thames Bridge or Golden Gate Bridge in USA or Howrah Bridge in Calcutta, there is a heavy traffic. Suppose at one part the bridge deck is getting deteriorated, there may be a small cavity or holes, potholes are formed. So you have to report the damages. For that, the repair material, best repair material is the SIFCON. You just occupy that area, clean that area, provide steel fibers, randomly distributed steel fibers over these potholes, infilter by the cement-based slurry, cement and fly ash or cement and silica fume. You allow the mix for about 1 to 2 hours. It will getting hardened. You open the bridge for the traffic. Your deck slab is as normal prior to the damage. That is the advantage. Rapid rehabilitation or repair and rehabilitation is possible by using SIFCON. Similarly for the pavement itself. One experimental investigation on RC frames with the SIFCON beam column joints. That is my experimental work for PhD thesis, doctoral thesis. We are investing for 2 big 5-story RC frames. That is the steel mold available. First, we are assembling the steel mold for the required shape. And we are preparing the steel reinforcement grill as per according to the IS 13920 detailing and designed according to IS 456 2000 practice. This portion is the foundation for the 3 columns. Left column, middle column, right column, and the beams are provided. These beams are normally designated as left beam, right beam, etc. 5-story beams, 1, 2, 3, 4, 5-story beams. So it is a reinforcement grill for the 5-story beams, 2-bay 5-story beams. This is the formwork for the 2-bay 5-story frame. This framework, this digital grill is inserted on the framework mold, plus forming the mold. So this fiber reinforcement grill is inserted in the mold like this. These plastic pipes are used for fixing the frame inside of the supporting foundation. This is the detailing of the reinforcement. As per IS 13920, the beam reinforcement and the column reinforcements are like this. You have to provide the development length LD plus 10 times the diameter length for the beam bars to be taken inside of the column. So the top reinforcement is having this development length and the bottom reinforcement of the beam has a development length inside. So LD plus 10 times the diameter. In between the junction beam column joint, you also provide the stirrups. That is the ties for the columns. So the stirrups, the reinforcement is considered interior reinforcement, longitudinal reinforcement. It will act as a stirrup for the shear reinforcement also. In order to measure the strain in the steel during experimentation, the small studs are welded to the steel reinforcement, tension rods and compression rods, etc. So small stud is welded to the main reinforcement. One stud is, 2 stud is sufficient for the tension reinforcement and another 2 stud for the compression reinforcement. For the beam slab also there are a set of studs available. These studs are normally covered with flexible ropes, hose pipes, in order to avoid the concrete making with steel. Bonding of steel and concrete is to be avoided for the stud. Bonding of stud with concrete is to be avoided. Then only it has a free expansion or free contraction. That is why the steel hose pipe, flexible rubber hose pipes are inserted. The fibers are round steel fibers. The fibers are procured in the form of rolls, and this rolled fiber is cut into small pieces having a length of 5 centimeters. The diameter of the wire is about 0.5 mm. So 100 is the aspect ratio. 100 is the aspect ratio. The fibers are packed inside here. Now, before starting the concreting, you have to make the cover concrete by means of SIFCON. So, in the formwork, you spread the fiber layers, randomly distributed discontinuous steel fibers are spread up to a thickness of cover thickness. Normally here the cover thickness is about 15 mm. So for 15 mm thickness, the steel fibers are pre-packed in this region, pre-packed in this region. That makes the cover concrete. Now the steel reinforcement has to be lifted up and placed over the formwork. The steel framework has to be lifted by means of crane and it has to be inserted into the formwork. So after that, you have to again make the fiber filling, that is the loose fibers, 5 centimeter fibers, randomly distributed fibers have to be spread over these areas and filled into the mold up to its full capacity, up to the top level. You might notice these small bits of column joints and not all the portion of the column and beam portions. So, in between this flexural beam, the concrete is placed and in the joint regions, steel fibers are placed, making SIFCON concrete. So, in between these plates, SIFCON joints, the regular concrete, M20 concrete has to be prepared and has to be poured and compacted as usual in RCC. And after making that concrete inside, the SIFCON is pre-packed steel fiber bed is infiltrated with cement-based distillery. Here, cement-based distillery is prepared in this. We are not adopting a pan mixture. At the time, the pan mixer is not available in the laboratory. So, pan mixing is done. And a thorough skilled person is making this flowable slurry, liquid slurry, and the slurry is poured into the fiber network. Once the slurry is very, very flowable, then only you follow the gap voids between the fiber. It makes the SIFCON material. Otherwise, there are honeycombs inside the SIFCON, it will not produce the enough steel. So the slurry is to be just like a water. And the concrete portion is vibrated by means of needle vibrator. This is done prior to the slurry pouring. After slurry pouring, the entire frame is finished, so it is subjected to curing for 28 days by gunny bags, spreading gunny bags, and frequently watered gunny bags. The gunny bags are always wet water bags, wet gunny bags. So the water is, this wet gunny bags prevent the evaporation of the water inside the SIFCON or inside the concrete to evaporate. So curing is 100% possible. So the companion specimens also inside, putting inside the formwork and this gunny bags and also cured in the same condition. It is not immersed in water, it is immersed in the same curing condition, gunny bag curing condition. After 20 days curing, the framework has attained, the concrete has attained its compressive strength, 100% compressive strength. It has to be lifted gradually from its horizontal position. This is the horizontal position. It has to be lifted by means of crane hooks to a vertical position and lifted to the testing bed. The frame is lifted to the transported to the testing bed. He is Dr. P. Govindan, my guide, PhD guide, and he is a good friend to mine when he is doing his PhD in IRTT. I am the MA student helping him for my MA thesis also. And this is the pre-packed, sorry, precast foundation block, and the foundation, the specimen test specimen is inserted into the foundation block. Now, meeting letter by means of the crane, it has been lowered slowly and inserted into the foundation block. The view of the foundation block is shown here. That is a precast foundation block having a slate, and the framework is placed inside the slate, inside the gap, and these are the holes to provide the 50 mm diameter steel bolts to make the connection, permanent fixity condition to the foundation block. This precast foundation block is bolted to the strong floor, which is the structural engineering lab strong floor, and it has been connected by means of the anchor bolts. 4 bolts on this side and another 4 bolts on the other side. That is the reinforcement details of the precast foundation blocks. While casting the foundation block, the holes are provided. Some steel pipes are inserted over the holes, and concrete is done. That is why these holes are available like this. In between, the steel pipes are there. That will avoid the friction between the framework and the foundation. Now the frame is ready for testing. The frame is ready for testing. That is the view of the frame after erection. These are the studs or the Dept points to measure the steel strain as well as the concrete strains. And some loading arrangements have to be fixed for applying the loads, and deflection arrangement has to be fixed for measuring the deflection. Initially, LVDTs are used, linear variable differential transformers are used for measuring the deflection. And after that, the cracking has been developed, and the large amount of deflection is measured by means of deflectometers, specially fabricated deflectometers. Before that, the frame is getting whitewashed and numbering is done. Left beam, right beam, that is beam 1, beam 2, beam 3, beam 4, beam 5, etc. LB1, LB2, etc. LB1, etc. This is left column LC1, MC1, RC1, LC2, RC, MC2, RC2, etc. etc. Because we have to note down the failure pattern, at which place the failure is taking place. For that, this abbreviation is necessary. Similarly, the strain gauge, the Dept points are also numbered. Dept points are also numbered to make the strain readings. There is the loading arrangement. Hydraulic jacks fitted with the ramps or extended ramps are used for applying the loads. And deflectometers or displacement meters are used for measuring the deflection. This displacement meter is used for measuring any number of displacements, say 1 meter, 1000 mm or 2000 mm or 3000 mm like that, because it is just like a protractor arrangement. This dial 360 degree, graduated 360. On spindle is there, inelastic thread, inextensible thread is passing, fitted at this point and passing through the spindle, and counterweight is there. Because of the motion of the frame, this counterweight goes down. Readings is indicated in the display. So you can measure any number of readings. The load is applied at 3 load levels: bottom, middle, and the top. Pumping unit is there and the distributing unit is there. By means of can pumps, the oil is pumped and it is distributed through the 3 jacks. Equal loads: middle, bottom, top. Equal loads has been placed on the 3 portion of the frame, and the load is indicated the back from displacement dial. This dial indicates the loads indirectly as kilometer. Because it is already calibrated, the ram diameter and the pressure is calculated, and the reading dial is proving ring is calculated, dial gauge is calibrated in kilometer. So 3 loads are there. So the 3 load summation of the 3 loads is the base shear. The base shear is up to some kilonewton, say for example 15 kilonewton, and unloading. And in the opposite direction, this is a push-pull jack. This action is push and this action is pull. For facilitating the pull action, the beam specimens are at the loading points are fitted with the steel rods, and it is tightened with the RCC frame. So whenever you pull the jack, it also pull the entire frame. So forward loading and reverse loading is possible. So one forward and one reverse. So this forms one complete cycle. Similarly, number of cycles have been done, gradually increasing the load level up to the ultimate load level. That is the cracking. Post cracking, some behavior is there. It's complete failure of the specimen. So this load sequence diagram. SR means SIFCON frame with a reverse cycle. We have also investigated another SIFCON frame only with forward loading, that is for the wind load. Base shear versus topsoil reflection. Load deflection diagram. Load deflection diagram. It is a hysteresis loop, forward loading, unloading, reverse loading, and unloading. So one loop is there for one cycle of loading. Similarly, number of cycles of loading is applied. The load deflection diagram is like this. Based on this shape of the load deflection diagrams, important parameters have been calculated. Say ductility factor for cycle 31 equal to the maximum deflection of the 31st cycle, maximum deflection of the frame at 31st cycle load divided by yield deflection. The yield deflection is defined as the deflection of the assumed frame. Assumed frame means the load deflection diagram of the stress strain diagram is non-linear, but you are assuming the idealized stress behavior or idealized load deflection behavior, that is the bilinear behavior. So the deflection corresponding to the bilinear behavior is delta y. Delta y is calculated like this. You draw a tangent to the first cycle of loading. You mark the another tangent from the ultimate loads. This is the intersection point. You measure the deflection. The deflection is 18 mm. So the yield deflection of that particular frame is 18 mm. Now the deflection here is maybe 5 mm, 10 mm, like that. And here the deflection may be 25 mm, 30 mm, 50 mm, 100 mm, like that. So delta divided by delta y gives the ductility factor. Similarly, for each and every cycle, the stiffness is calculated because it is a cyclic load. You are measuring the stiffness at the ratio of P by PU equal to 0.7 to 75% of the maximum load. Draw a tangent and measure the slope of the tangent. It gives the stiffness as 2 kN/m. So the basic load deflection diagram, base shear versus load deflection diagram, is very important. Load deflection behavior. This behavior has been converted into monotonic behavior by taking the only peak points. So this is the curve. There is a forward loading. Similarly, for the reverse loading, this is the load deflection diagram for the reverse loading. So like this or like this. Similarly, you are measuring the deflection at 5 levels. 1, 1, 2, 3, 4, 5. So 5 deflections are available for each story. First story deflection, second story deflection, etc. And if you plot the deflection profile, delta 1, delta 2, delta 3, delta 4, delta 5 during forward loading, At the level of loading is 62.4 kN. This is the deflection profile. Same 62.4 kN or another load, say 70.2 kN. In the opposite direction, the deflection profile is like this. Negative deflection in like this. Similarly, for the other 124 kN or 145 kN or 190 kN like this, the deflection profile is there. If you plot all the lines, it will give a displacement like this. You may see the coconut trees oscillating due to the wind or cyclone like this. The same profile is established here. It is the deflection profile of the frame subjected to earthquake, subjected to seismic forces. Simulated earthquake forces. Not we are applying the actual seismic load, it is simulated. Now the stiffness values are plotted, and for each and every cycle, the stiffness values is decreasing through forward cycle and as well as the reverse cycle. So it is called as stiffness degradation. Stiffness degradation. Ductility factor with stiffness is defined as the load required to cause unit deflection. So W by delta, that is the slope of the tangent, is taken as the stiffness. Ductility factor versus load cycles. Similarly, ductility factor has been already calculated, delta by del y, delta y. This has been plotted for various load cycles, up to 40 load cycles. The variation is just like this. There is another parameter called as cumulative ductility factor. This is cumulative ductility factor is nothing but the summation of the individual ductility factor, forward ductility and reverse ductility. If you add both the ductility, that is for the one cycle, complete cycle of loading ductility. Similarly, second, third, fourth, etc. This reading has been numerically added, not algebraically added. It is numerically added, and all the ductility values are plotted against load cycles like this. For initially 0 ductility, and the ductility goes on increasing, and at the ultimate cycle of loading, the ductility value is about 250 like that. The ductility of the Sifton frame is about 250. Similarly, the energy absorption. Energy absorption is calculated as the load deflection area under the load deflection diagram. This is the load deflection diagram. So, if you calculate for last cycle of loading, you plot this graph in graph paper, graph sheet, and measure all the interior squares and multiply with the units. You get the total energy, total area under the load deflection diagram. This total area under the load deflection diagram is called as the energy absorption capacity. So, for each and every cycle, the energy absorption capacity is calculated, and it is plotted as relative energy absorption capacity. Relative energy absorption capacity like this. And if you add this all relative energy, you get a cumulative energy absorption capacity like this. So, at the ultimate cycle of loading, the total energy is like this. Kilonewton mm. Kilonewton mm. In ductility, it is kilonewton. Sorry, ductility, there is no unit, it is a numerical unit. There is a failure pattern of the frame. Whenever you load the frame is deflecting up to the frame, cracks have been formed, and spalling of the concrete or the yielding of the steel has been observed, and finally the cracks have been developed very much, and the failure pattern is observed. That is the crushing failure of the concrete. At the bottom of the foundation and the column. There is a column and foundation. This will be the crushing failure of the concrete. Similarly, at the middle story level, the frames are swinging like this. So, positive failure and negative failures are taking place. This involves the cracking, forward cracking and reverse cracking. So, X-type cracking is possible, and this is the failure pattern. Here at the junction of the beam column joints, plastic hinge is formed and complete rotation is possible. The rotation of plastic hinge causes the distribution. That is the final view of the frames. That is the RC frame. For the comparison purpose, RC frame is cast and tested. Similarly, the FRC frame and SIFCON frame is cast and tested. You just compare the SIFCON frame and this for ultimate failure. For RC frames, the shear strength of the concrete is very low. So at the junction, beam column junctions, the concrete is unable to withhold this shear strength. So it causes the failure of the spalling of the concrete or failure of the concrete in the junction regions. Whereas at the exterior portion, this and this plate, there will not be any shear force, only the flexural failure. So the failure is only at the interior beam column joints. Close view of the failure pattern. This is RCC, conventional RCC. But if you provide FRC or SIFCON, there is no spalling of concrete at the junction, beam column junction. Only the cracking has been done. There is red cracking is forward cracking and the green cracking is reverse cracking. So extra cracking is possible. There is no spalling of concrete inside the joint. You just compare the forward loading and the reverse loading. Beam column junction, particular beam column junction MC1, forward loading means the frame is moving in the forward direction. This is the failure structure of a beam, failure pattern of a beam. The same junction, when it is pulled back, that is applied by the reverse loading, it is pulled back. So the column moves in opposite direction. Here it is in the right direction, here in the left direction. So the joint is also moving in the left portion. The tension and compression are developing in opposite phases. Inga tension vandu bottom la vanda, inga tension vandu top level. So this is the crushing failure of the beam column junctions due to forward loading, due to reverse loading. At the exterior beam column junction, due to the reverse loading and forward loading, the failure pattern is like this. Complete concrete is fallen off. Only the steel reinforcement is getting yielded and plastic stick have been formed. Plastic hinges have been developed. So the plastic hinges have been developed at the left junctions and the right junctions of the beam. The use of SIFCON in the hinging zones of RC frame subjected to lateral static cyclic loading results in 100% increase in first crack load, 100% increase in cumulative ductility, 100% cumulative energy absorption. So this cumulative ductility and cumulative energy absorptions are about 100%. So the use of SIFCON in the beam column joints of the condenser frame has resulted in better ductility and better energy absorption. And these qualities are desirable for structures located in wind or earthquake prone zones. For seismic zones, these qualities are required. That is why these SIFCON beam column joints are provided in the seismic zone 5 or in the wind zone, topmost wind zones, such as in coastal areas. You may know that due to the Coil or the recent Coil attacking Odisha, majority of the structures are attacked by the 155 km speed wind or 200 km speed wind. So a lot of damages are there in RC frame structures. These damages have to be prevented by means of this fiber reinforced concrete or SIFCON. Another experimental investigation. In this investigation, hybrid fiber reinforced concrete is used. One is steel fiber and another is glass fiber. Round crimped steel fibers, rectangular 3S fibers and glass fibers. These two fibers are mixed as HFS1 and these two fibers are mixed as HFS2. 1% steel fiber and 0.02% rectangular 3S fibers and 0.02% glass fibers, etc. The mixed proportion is like this. Silica film is added as mineral mixture because the concrete grade is high performance concrete. 0.02, 0.03, 0.04 glass fibers, etc. Details of specimens, cubes, beams, and columns, beam column joints, etc. This beam column joint is 1/5 model of the prototype structure, 1/5 model of the prototype structure. And this beam is subjected to 4-point loading, 2-point loads on this point, flexural behavior, pure flexural behavior. And column is subjected to axial compression and the compressometer, by means of compressometer, the compressive strain is marked and stress strain diagram is marked. And beam column joint, reversible load is applied. This is a forward loading and this one is the reverse load. Forward loading and reverse load. So based on the experimental results, the compressive strength has been improved 45 Newton per mm square for the plain concrete to 58 Newton per mm square or 61 Newton per mm square for high performance concrete, hybrid fiber reinforced concrete. Split tensile strength 2.8 Newton per mm square, 4.24 Newton per mm square. Nearly 50% strength is observed in HFR-1. Whereas flexural tensile strength 4.7 Newton per mm square for plain concrete and 6.68 Newton per mm square for HFR-C and 5.88 for SFR-C steel fiber reinforced concrete. This results in about 42% in HFR-C1 and 32% in HFR-C2 when compared to plain concrete. Similarly, we compared it to steel fiber, the percentage is increased by about 11%. Stress strain behavior of the hybrid fiber reinforced concrete is similar to that of other concretes, but the modulus of elasticity is slightly improved because of the high strength. Behavior and mode of failure is that this is a plain concrete splitting failure, but here there is no splitting failure into two pieces. Only cracks have been found. Durability is measured by means of the RCPT apparatus, chloride in ion penetration test. 60 volt is applied for the specimens. The readings are noted down every 30 minutes and charge passed is noted down by using Topsider formula. And the graph shows that total charge passed. For the plain concrete it is 1800 and for HFR-C it is only 700 or 800. So it means the category is low to very low. This is low category and very low category. But normally the concrete is moderate category. But here in the laboratory investigation, we are making a perfect concrete with a low permeability, incorporating silica fume and other things. So it gives a load. So the beams are subjected to loading, cyclic loading. There is a load deflection diagram. Load carrying capacity, ultimate load carrying capacity is very much improved, 45 to 51 kN, and ductility is 16 to 30, near about 80% or 90% improved in ductility, and the energy absorption 700 to 1900, more than 100% improved. 1.77 times and 2.6 times. The energy absorption capacity is about 2.6 times, 160% increase. The mode of failure for all the beams. Similarly, for the beam column joints, that is a load deflection diagram. Load carrying capacity is improved like this. The ductility is 11 and 23, 100% increase in ductility, 100% increase in absorption, 293, 300, 769. 100% increase in energy absorption capacity. And the mode of failure pattern is like this. There is a plain concrete, several cracks are there. The crack width is more and more. You can clearly notice the crack width is more than 0.3 mm and 0.5 mm. But in HFR-C, the crack, there are numerous fine cracked materials, fine cracks are there, parallel cracks. The width of the crack is less than 0.1 mm and the joint is failed by developing the beam plastic hinge mechanism. So the general conclusion is such a first specimen exhibits a significant increase in ductility and energy absorption capacity when compared with conventional specimen. Instead of adding a single type of fiber, the combination of different types of fibers increases the ductility and energy absorption capacity. This phenomenon is particularly advantageous in case of structures located in background zones. Another investigation, still fibers and natural fibers such as vegetable fibers, banana fibers are added inside. This banana fibers is extracted from the banana tree and it is treated with alkaline sodium hydroxide solution, alkaline solution to treat as a fiber. So this is a process of making the banana fiber. This one is the sewing of the banana fibers. Normally, these banana fibers are now used in textile as the eco-friendly cloths instead of the cotton fibers. These banana fibers are also used in weaving purposes. The alkaline treatment purpose means about 5% sodium hydroxide or 10% sodium hydroxide solution is used inside, and 4 hours immersion is possible. And because of this 4 hours immersion, the fiber are getting toughened, and this figure shows the treated fibers. These fibers are cut into the required length and used in the compound. This fiber volume fraction is 0.5% by weight of the cement. Here 1% by volume of concrete. 1% by volume of concrete. இங்கே 0.5% by volume கிடையாது, 0.05% by volume or 0.5% by weight of cement. The stress strain behavior is like this for the FRC, and beams as usual, the cyclic load deflection behavior, and the load carrying capacity is for RC beam it is 45 kN and 51 kN, etc. The ductility is increased and the energy absorption capacity is increased like this. The stiffness degradation is like this. There was 30% increase in compressive strength as a result of hybridization, because the high elastic modulus of steel fiber and the low elastic modulus of banana fiber work in perfect combination. Hybridization boosted the split tensile strength and flexure strength by 45% and 65% respectively. The higher number of fibers bridging the diameter splitting crack, the higher will be the split tensile strength. Yeah, 60% increase actually high number of fibers. Large number of fibers are inside that. Similarly, instead of banana fibers, sisal fibers are used. Sisal fibers is planted in this agave plate, and the fibers are made, and it is treated with alkaline hydroxide solution, sodium hydroxide solution. And these fibers are, sisal fibers are having the properties: length 25 mm, diameter 0.25, aspect ratio 100, tensile strength 260 Newton per mm square, and the modulus of elasticity 42.5 GPa, and density 1.7 gram per cc. And the compression of result source is 40 Newton per mm square for conventional concrete, and for the hybrid 54 Newton per mm square. Nearly 50% strength is increased. Similarly, for the split tensile strength 3.67 and 5.52, here also about 50% increase in tensile strength. For the flexural strength 6 Newton per mm square and 9 Newton per mm square, here also 50% increase in strength due to the hybrid fiber. Mono fiber, sisal fiber is 7 and steel fiber is 8.87. Compared to this mono fiber, it will be improving. About 10% is improving. There is an experimental investigation of the hybrid fiber reinforced concrete beams made with sisal fibers. 2-point loading is applied, 15 kN, and ultimate load is 45 kN. So the crack load is increased by 20%, 30%, etc. 22.5 kN, and the ultimate load is 51 kN. Load deflection diagram and ductility factor, variation of ductility factor with the load cycle, variation of cumulative energy absorption with the load cycles, and mode of failure. Here you note that only a very limited number of cracks, therefore inclined cracks. But here about 90-degree straight cracks or dark flexural cracks. Number of cracks are available because of the fibers. By adding these hybrid fibers, the flexural tensity has increased by 64%, and the first crack load capacity is increased by 50%, and ductile factor is 86%, energy absorption is also 86%. Instead of adding a single type of fiber, the combination of different types of fiber increases the ductility and energy absorption capacity substantially. This phenomenon is particularly advantageous in case of structures located in attack-prone areas. This investigation is stainless steel fiber. You may call steel fiber means it is subject to corrosion. So, in order to study the corrosion property of the steel fiber, we are using the stainless steel fibers and done the experimental investigation. By inducing corrosion, that is the accelerated corrosion testing apparatus. 12-volt current is applied, that is a cylindrical specimen, and the rod is projected. This rod is embedded in the concrete specimen, and it is connected to the positive terminal of the voltmeter. And a stainless steel plate or aluminum plate is used as a cathode, and it is connected to the negative terminal. 12-volt current is applied for accelerated corrosion, or normal corrosion, 6-volt or 5-volt corrosion application is sufficient. So that is the schematic diagram, the reinforcement half cell potentiometer. Half cell potentiometer, copper sulfate solution and the copper electrode, that is a half cell unit. So you are measuring the potential EMF reading, and it will indicate the rate of corrosion. That is the multimeter, and you are in half cell reading, that is the electrode half cell potentiometer, and it is just to make touch on the concrete surface, and the steel rod is connected to this. It will give the values, the readings. Originally, there is no corrosion, so all the readings are positive. And after some times of accelerated corrosion, it is immersed current applied, the reading becomes negative and propagate further and further. So, at the end of 140 hours, minus 387 and minus 226, according to ASTM standards, if it crosses minus 350 milliwatt, then it's a chance of 95% corrosion. So, for the steel fiber reinforced concrete beam, corrosion will start at 140 hours. But for stainless steel fiber concrete, the corrosion is still not started. It is uncertain corrosion. There may be a 50% corrosion or 40% corrosion, etc. You have to wait up to about 200 hours. It crosses minus 350 readings. So that is the advantage of the using conventional steel and stainless steel. That is a specimen, corroded specimens. This graph shows the improvement given by the stainless steel. That is a stainless steel. So it that is the steel fiber. It crosses the stability rating minus 350 milliwatts at 140 hours. At 190 hours, the reading may be about 700. The corrosion will entirely cause a complete deterioration of the reinforcement, damage to the reinforcement. But SSFRC, the reinforcement is getting corroded just starting minus 350, and for reaching 700, it may take about 300 hours or 500 hours or 700 hours, etc. So, for getting more corrosion resistant performance, FRC is preferred with the stainless steel fiber reinforcement. There is a load deflection behavior, load carrying capacity, cumulative ductility and energy absorption. That is the test setup in the laboratory. Beam column joint. That is a test setup in the laboratory. The load deflection diagram. The load carrying capacity, deflection, ductility, energy absorption capacity diagram. And mode of failure is like this. Similar to all modes, the plastic formation is taking place at the beam column junction. Close up view of the beam column junction. SSFRC exhibits enhanced durability properties than that of conventional concrete and SFRC. The percentage loss incident under acid attack is 10% for conventional concrete, 7.4% for SFRC. and 5.65 for the stainless paper. That is the acid H2SO4 solution. It gives offer more resistance. Stainless steel fiber reinforced concrete gives more resistance. Similarly, the initiation time for corrosion is 190 hours for exhibiting better resistance. Ultimate load carrying capacity, ductility factors, stiffness, like that. There are several advantages of it. Based on this, the outcome is for seismic behavior, use of fibrous concrete is needed. The effect of adding stainless steel fiber not only influences the behavior of beam crown joint by increasing ductility characteristic and energy absorption characteristics, but the durability characteristics and energy absorption characteristics also improved notably. That is stainless steel fiber use panna durability improved. That is another type of experimental investigation. In this polypropylene fibers are added. Instead of vegetable fibers, polypropylene fibers are added. That is the view of the specimen before and after H2SO4. Complete deterioration of concrete is taking place. Cement mortar is completely eroded. Only the aggregates are visible. Half-cell loading and corrosion. The same result is obtained here also. Enormous ductility and enormous energy absorption. So hybridization boosts the split tensile strength and fluctuation by 60%. The ultimate load characteristic of hybrid fiber reinforced concrete being with steel and polypropylene fiber has been the highest values of 52.5 kN, 16% increased. Ductility is about 1.6 times greater than the conventional concrete beam. The energy absorption capacity is about 2 times greater than conventional RC beams. Addition of hybrid fibers generally contribute towards the energy absorption mechanism, bridging action, whereas the non-metallic fibers, polypropylene fiber, resulted in delaying only the formation of microcracks. This polypropylene fiber or vegetable fiber will not act in the ultimate zones. It is acting on the initial formation of the microcracks. And in the macro cracks, the bridging action is done by only the steel fibers. In the hybrid fibers also, polypropylene is acting in the initial stage and the steel is acting in the final stages. Hybrid fibers are more effective in the crack reduction compared to individual steel fibers. Addition of non-metallic fiber increases the availability of fiber content in the concrete. So that is the brief presentation on fiber reinforced concrete. In this presentation, we have noted the definition of fiber reinforced concrete, mechanism of fiber reinforced concrete, advantages of fiber reinforced concrete, application of fiber reinforced concrete, and the recent developments in the fiber reinforced concrete, ductile fiber reinforced cementitious composites. In this ductile fiber reinforced cementitious composite, the mineral admixtures are added to improve the performance of the concrete. And the steel fibers, instead of monofiber steel fibers, we are adding a hybrid fiber consisting of low modulus fiber and high modulus fiber to improve the seismic behavior of the fiber reinforced concrete. So all these results showing the same result. The fiber reinforced concrete is used in seismic resistance sections because of the increase in ductility properties, increase in energy absorption properties, which are essential for earthquake resistance sections. So thank you very much for your patient listening. You may opt for questions.
Participants can post their queries in the chat box, or I can directly ask to the sir.
Thank you so much, sir, for your wonderful presentation. Thank you for accepting.
Thank you, madam. Thank you.
Participants, if you have any queries, you can post in chat box.
Actually, this presentation is based on the research experience which I have got from IRTT. Actually, I have taken the classes for ME students and PhD students for the past 15 years, from 2003 to 2018. So during that period, our students are working on different types of special types of concrete on this results. The fiber reinforced concrete, combination of hybrid fibers, combination of steel fibers with the cooked and dripped steel fibers, which is macro fibers and microfibers. So there are a lot of potential opportunities for research in this fiber reinforced concrete. Without the fiber reinforced concrete, there will not be any high performance concrete. So it is our compulsory to use fibers inside the concrete in order to improve the properties. Ordinary concrete la poi waste material la poi research பண்றத விட fibers add பண்ணி உங்களுக்கு improved properties கொடுக்கிறது. Any questions from participants? How to avoid balling effect in carbon fibers? The balling effect depends upon the volume fraction of the fibers. For steel fibers, if you adopt 0.5% or 1% or 1.5%, there will not be any balling effect. But at the same time, if you go for 2.5% or 3%, the fibers are plugged together, giving a balling effect. The same thing is also applicable for any other thing, glass fiber or carbon fiber or polyester fibers or any other thing. So you have to use only the optimized volume fraction of the fibers. You take an exhaustive literature review and find out the optimal value of the optimum volume of the fibers and provide only this optimum volume. Whenever you exceed, the fibers will not act as a randomly distributed fiber. It will be plugged together and giving the balling effect. It will not be a fine fiber reinforced concrete. It will be ordinary concrete, not a fiber reinforced concrete. So balling effect can be prevented only with low volume fraction of the fibers. Madam, okay? Frida, madam. Where do we get feed? Frida, madam? Okay, the remaining.
Thank you, sir.
Thank you. Thank you. Your doubt is clear or not? Madam?
Yes, sir. How to confirm the dispersion of the fibers, uniform dispersion of the fibers, sir?
Okay, thank you. But you have to be very careful in selecting the fibers, selecting the mixed proportion, selecting the proportion of the volume fraction of the fiber, and mixing, placing, etc. You have to avoid the balling effect based on the result of careful mixing, careful placing, etc. Okay, thank you for your
Sir, I have one question, sir.
Okay, thank you.
Sir, can we use this fiber reinforced concrete in ordinary construction, that is a normal residential building construction?
Actual, my investigation and our previous researchers are telling that you should use fiber reinforced concrete in our normal structures. Then only you get the improved properties. For example, if you want to construct a multi-story buildings, columns, beams. Column is erected up to the floor level and beam is built and monolithic junction, beam column junction is fabricated. Then only you proceed with the second story, third story, etc. So at the beam column junctions, if you provide fibers inside the mix, that is you are preparing M30 concrete or M20 concrete as usual in the way batch or in the site mix. But if you add some fibers, steel fibers or the glass fibers or carbon fibers, any type of fibers, steel fiber is cheapest fiber available compared to carbon fibers or basalt fibers. So these steel fibers are added up to about 0.5% volume fraction. 0.5% of volume fraction means you calculate the volume of the concrete inside the mold, just take the 0.5% and multiply it by the unit weight of the steel fiber. It gives the total weight of the fiber you add on the mix. That volume, that weight of the fiber have to be weighed and inserted into the mold. That is the mixture. You get a fiber reinforced concrete. That fiber reinforced concrete is placed inside the beam column junctions. It will give ductile behavior or flexible behavior during the beam or during earthquake. So during wind or during earthquake, there will be a large amount of shear strength or reversible strength, produce reversible load, reversible forces produced inside the joint. You have to avoid these forces by means of the enhanced strength, ductile and absorption capacity.
Sir, these fibers are commercially available or we have to prepare, sir?
These fibers are commercially available. You search in India Mart or you search in factory. For example, steel fibers, there is one company, Kasturi Metal Mart in Pune. They have supplied the crimped fiber according to your specifications. Similarly, flat fibers, Shaktiman steel fibers and other fibers. There are several types of steel fibers available in the market. Similarly, polypropylene, polyester, polyester means recurrent trace fibers and glass fibers. In Coimbatore itself, you can get the glass fibers and the polypropylene fiber from Sinanko, Gandhigram, 7th class street, Sinanko. You can get the glass fibers. Or by searching through the internet, India Mart, they will supply the fibers. All types of fibers are available, except basalt fibers. These basalt fibers are not commercially available. You have to import the fibers from the foreign countries.
Okay, sir. Thank you, sir. There are some more questions in the chat box.
How can be uniformly mixed fibers in concrete? Thus, segregation occurs while mixing. Christian bias. Okay, if you adopt steel fibers have density 8 gram per cc, so there is no mixing problem. You can directly mix on the dry concrete, adding into the mixer or adding into the hand mixing is adopted means adding at the final stage, hand mixing. But if you adopt for recurrent trace fibers or polypropylene fibers or any other synthetic fibers, coir fibers, etc., not vegetable fibers, but the synthetic fibers, this aspect ratio is about 600 or 700 because the length is 12 mm or 25 mm and the diameter is 0.00 something, very, very small hair lengths, a little bit less than the hair length. So this type of fibers will not be added directly. You can disperse in the mixing water. The fibers are uniformly dispersed, and then you add this fiber content water to the concrete mix. That is the uniform mixing procedure for the synthetic fibers. For vegetable fibers, you can directly add it because it will not affect the mixing procedure. But uniform mixing is done. You have to ensure by at the last stage of the mixing operation, not at the beginning stage, last stage. Let us say 1 or 2 times mixing time, not less than 1 or 2 minutes. Uniform mixing available. Balling effect varadu. Fiber volume fraction kammiya irundha balling effect varum. Mixing வந்து uniform எடுத்துக்கலாம். Trial and error வேற ஒண்ணும் இல்ல.
Sir, one more question, sir. Any criteria for selection of fiber?
High modulus and low modulus fibers. உங்களுக்கு வந்து எர்த்குவேக் பிஹேவியர்ல வேணும் அப்படின்னா ஹை மாடுலஸ் ஃபைபர் போடணும். அது வேண்டாம் எனக்கு சிரிங்கேஜ் கிராக்ஸ் பிளாஸ்டிக் சிரிங்கேஜ் இந்த பிளாஸ்டிங் போடுறோம்ல நம்ம வீடுகளுக்கு பிளாஸ்டிங் பண்ணுறோம் மேசன்ரி பில்டிங்ஸ் அந்த பிளாஸ்டிங்ல நிறைய கிராக் இருக்கும். அந்த கிராக் எல்லாம் அரெஸ்ட் பண்ணணும் அப்படின்னா சிந்தட்டிக் ஃபைபர் லோ மாடுலஸ் ஃபைபர் பண்ணும்போது ரெக்ரான் 3S ஃபைபர்ஸ் கமர்ஷியலி அவைலபிள் 125 கிராம் பேக் அவைலபிள். அதை நீங்க கடையில இருந்து வாங்கிக்கிங்க. ஒரு மூட்டை சிமெண்ட்டுக்கு அந்த ஃபைபரை ஆட் பண்ணி நீங்க மாற்று 1:3 1:5 மாற்ற ரெடி பண்ணிட்டு அதை வச்சு பூச்சினீங்கன்னா கிராக்கே வராது. ஸ்ரிங்கேஜ் கிராக்ஸ் இல்ல பிளாஸ்டிக் ஸ்ரிங்கேஜ் ஆர் ட்ரைன் ஸ்ரிங்கேஜ் எந்த கிராக்கும் வராது. செவரு நல்லா இருக்கும், ஃபினிஷிங் நல்லா இருக்கும், அஸ்தட்டிக்கா இருக்கும், கிராக்கே வராது. This is already used in commercially by all the contractors.
Sir, one more question, sir. Good afternoon, sir. Will adding fiber to the concrete affect the mixed design?
இல்ல mixed design ல ஒன்னும் affect ஆகாது. At present, there is no mixed design for fiber reinforced concrete in India. IS code இதுவரையில சொல்ல கிடையாது. இத்தனை வருஷமா அண்டர் ரிசர்ச்ல தான் இருக்கு. அதனால நீங்க என்ன பண்ணணும், ஆர்டினரி கான்கிரீட் ஆஸ் யூசுவல் டிசைன் பண்ணிட்டு அதுல ஃபைபர் வால்யூம் ஃபிராக்ஷன் எக்ஸஸா ஆட் பண்ணுங்க.
Okay, sir. Thank you, sir. I think there is no more questions, sir. Shall we can conclude the session, sir.
Okay, thank you very much for giving this opportunities. Thank you.
Thank you, sir.
Now,
Thank you for your wonderful presentation and accepting our invitation, sir. Thank you all. A feedback link is shared in chat box. Kindly fill it.
now we came to the end of the session. I am really very happy to propose the vote of thanks for this webinar. First, I would like to thank the management and principal of Dr.N.G.P Institute of Technology for the permission and facilities provided to organize this webinar. And I would like to thank our resource person, Dr.G.S.THIRUGNANAM sir, for spending this valuable time and a brief, interesting and informative speech on fiber reinforced concrete. Thank you, sir.
Thank you.
I express my sincere thanks to our HOD madam for the support and guidance to organize this webinar. Thank you, ma'am.
Thank you, sir.
I thank my colleagues for their help and cooperation to organize this webinar, and special thanks to Shankar. Thank you, Shankar. I express my heartfelt thanks to all the participants from various organizations from various states across the country, without whom the event would not be a successful one. Once again, I thank everyone behind this successful event. Thank you all. Jai Hind.
Okay, I take leave.
Participant, fill the feedback link as early as possible. Thank you all. சங்கர்
சார்
நீங்களா போஸ்ட் பண்ணிடலாமா?
சார் கட் பண்ணிடலாங்க சார். அவ்வளோதாங்க சார்.
ஓகே சார், தேங்க்யூ சங்கர்.
ஓகேங்க சார்.